Wonderful. I'll take it from here. Well, it's the first time I've actually held a webinar, and I gather that I have an audience all over the world. And on this first picture here, you actually see the picture of my campus in Colorado, but then you say it says Berlin underneath. I am currently in Berlin, and Berlin happens to be my hometown. I'll say a few words about myself. I received a mechanical engineering education in the US and in Germany. I then spent 5 years at Johnson Controls in energy consulting and spent a year at the Fraunhofer Institute for Solar Energy Systems in Freiburg. I joined the University of Nebraska to start the architectural engineering program in 2008. I then, in 2008, I moved to Colorado and have been there ever since. I had a chance to spend another year on sabbatical in Spain. I have started a small firm called Q Coefficient in 2008, for whom I'm co-founder and chief scientist. And being in Boulder, I have a chance to work a lot together with folks at the National Renewable Energy Laboratory, and that allowed us to start the Renewable and Sustainable Energy Institute in 2009, of which I'm now associate director. So with that, let me jump into what we're going to cover today. So historically, building energy modeling has been used for comparison purposes. It has been used for design assistance, and we really didn't have a reasonable expectation that the operation that we have captured in the model would match true building operation. But recently, there's been a shift in modeling. We see a shift from modeling buildings as designed to then as built as we accumulate some operational data. And increasingly, we expect more of the fidelity of a building energy model. And to achieve that, we need a specification of the building operation. And state-of-the-art building energy modeling programs do allow for some representation of control strategies, but really complicated, sophisticated control strategies like dynamic pressure set point reset, demand controlled ventilation that actually captures the occupancy in the building, a little harder to model, if not impossible. So this chapter 14 in the book is on the role of building automation, and it's on model-based control, which are problems in which a process model is harnessed to guide operation either of a part of a building or the entire building. It's interesting to note that in such a control-oriented model, that model would be used in the building's automation system. But in order to function well, relevant control aspects of the building automation system must also be in the model. So there's this interesting reaching from the real world into the model and back into the real world. So today I'll take the time to introduce you to some aspects of model-based control for buildings. And I begin with a perspective in which we try to mimic the control of a radiantly cooled commercial building, utilizing detailed building performance simulation to minimize energy consumption and to see what could be achieved through proper control from a supervisory perspective. The context from which we're viewing this is a low energy design that is kind of state of the shelf, less so state of the art. The type of building that you see here that's equipped with thermally activated building systems for both heating and cooling, with displacement ventilation, with a dedicated outdoor air system, some ground source heat exchange to serve a reversible heat pump. All that is pretty much state of the shelf, and I would say from my knowledge of the European market, pretty much 50% of commercial office space is now designed using such radiantly cooled buildings, cooled and heated buildings with substantial amounts of thermal mass. So one of the first things that was realized is that controlling those buildings is difficult. And the approach we're taking here is to harness a model to optimize the building with respect to some objective function. And we're basically looking at two approaches to this so-called model predictive control. On the left-hand side, and I'll use my cursor a little bit, you'll see it. On the left-hand side, you see the case of online or real-time control. Here we have a model, and the model is a control model that is simpler than the actual building or omits certain aspects that are not necessary. And in this closed loop here, you can see an online model predictive control system that tries to find the best control strategy U star, sends it to the building, and the building tells about itself through the state feedback vector X. And we do this in continuously. But to do this in the time constraints, we often have to use simpler models, make modeling simplifications, and we also have to contend with model mismatch as a result, and we have to contend with imperfect predictions. Now, juxtaposed to that is on the right-hand side is offline MPC, in which you can see we have a model of a building and we apply the optimal strategy to this very same model. So we have a simulated response that equals the control model response, and that allows us to contend what happens if we have perfect predictions, if we have no time constraints, if we have no model mismatch. We have, so to speak, idealized ivory tower conditions. We applied this approach that you see on the right-hand side, the offline approach, to Energy Plus. And in Energy Plus, we unfortunately do not have thermal states available. And as a result, we have to do something to let the building know where it is. And that is, we have to initialize the building through this initialization horizon that you see here. And over this cost horizon, considering the building has thermal mass, we are trying to plan a strategy, but recognize that it has an impact into a time beyond the planning horizon, which is the reason for maintaining this termination horizon. That is not occupied by any plans, but together we're trying to optimize an objective function, and in this study, this energy. Once we have found an optimal strategy, we send that to the same model. In the offline case, it's the very same model. We execute the strategy. Now, that part of the history that is here labeled execution becomes part of the initialization now for the next time step. And we resume the same process. We make a new plan that minimizes the cost over the next horizon, and we march through time in this particular fashion. So that is a process that we have implemented utilizing a MATLAB-based optimization environment. In this optimization environment, we create an input file, and that input file is read by the optimizer. The optimizer then creates a candidate vector of decisions. Based on those, we create an Energy Plus input file. That input file is then simulated by Energy Plus, and we check how good it performs based on some fitness criterion or exit criterion. And if it isn't doing all that well, we have to repeat this until we find a solution, and that solution then is saved and is sent to, or is deployed in the simulated building for this offline scenario. As a case of application, I'd like to offer a scenario in which we look at a smallish building, and the building has 11 thermal zones. It has 3 floors. It is massive, as well is well insulated, and is equipped with automatic exterior shades. The HVAC side of things contains a dedicated auto air system with a heat recovery ventilator and associated heating and cooling coils. We have 4 heat pumps with ground source connection. We have 11 individual constant volume radiant hydronic circuits in the ceiling that provide the radiant cooling and heating. And we're utilizing heating and cooling set points based on EN 15251 for a Class B type building. We compare ourselves in this study against the work accomplished by Bjarne Olesen several years ago in the early 2000s. For several years, he investigated this problem, and he developed an approach to generating separate heating water and chilled water, supply water, temperature reset curves, and that has been deployed in numerous buildings. So for this task of energy minimization, let's look at 1 week that begins with a weekend. It's a week in April, and I point to the upper graph right now, which has 2 days, Saturday and Sunday, in which not much seems to be happening. And by the gray line shows the outdoor air temperature on the secondary y-axis here. You can see that over the course of Monday through Friday, the building that is governed by the optimal controller tends to have temperatures that are shown in blue. They're lower temperatures. The air and operative temperatures are lower for this building than for the base case building utilizing the standard control. In general, we see temperatures about 2 Kelvin less. What's happening on the HVAC side is shown in the graph below. You can see that the standard or base case control are the circles, the relatively high temperatures. They go from high temperatures to low temperatures back and forth based upon the reset rule that was developed. The optimization, however, chooses significantly lower temperatures shown in the blue crosses. You can see those are significantly cooler. And furthermore, the optimizer has control of the circulators, the pumps, and those are being turned off and on. And there are certain times when they're not running at all. So it recognizes that this pulsed operation might be useful. The height of the pump here indicates what fraction of the hour the pump is running. It may be 10 minutes out of the hour, it may be 60 minutes out of the hour, but you can see that the optimizer is very sparing in the use of the pump as well as hot water in supply of this building. So we see that the optimizer actually chooses to disable circulators and run them for shorter time periods, which is in fact a process that is utilized today by many radiant cooling and heating designs. They actually pulse the building instead of running the pumps continuously. So the optimizer found that. The energy impact of the different operations shown here, you see on the top, the same week you see large blue bar graphs for cooling consumption and red for heating. You can see in the base case control we have significant switching between heating and cooling in alternating fashion, and it doesn't take much imagination to realize that that is a problem that is found in many taps conditioned buildings, especially during the transition time periods of the fall and the spring, where exactly that type of alternation between heating and cooling is observed. The optimizer for this very week uses the circulators less and has much smaller heat pump loads, and you can see there's a little bit of cooling required, but not more. So how's the building performing from a comfort perspective? What we see here is that the building is on the basis of a PMV-PVD, predictive mean vote, percent people dissatisfied model. We are keeping the building in the gray zone. That's the plus minus 0.5 zone that ISO 7730 suggests. Whereas the standard building seems to exceed the indoor conditions, tends to be slightly warm. The optimizer keeps the building right where it should be. Together, if you take one minus the other, the optimizer has the savings on the negative side, leading to an overall weekly energy savings of 51%. A figure that I would say is encouraging to further pursue this kind of a optimized control for radiantly conditioned buildings. In this next project, we are shifting gears from minimizing energy to a cost perspective. In particular, we're looking at a larger commercial building responding to price information. And we are basically resuming the optimization sequence, but now it's for an online case in which, in addition to the optimizer, we now have an actual building showing on the left as a little circle, and we have weather information. And the way things proceed is we first get information on the weather from, in this case, the National Oceanographic and Atmospheric Administration, and then we go through the same process as before until we find an optimal solution. When we find this optimal solution, we store the result, but we also send it to the building in question, and that building executes that set point or that control for the next hour. And this is being done in real time in a cloud-based software as a service infrastructure. So if we look at an example conducted for the city of Chicago, this chart shows the outside air temperature reaching about 90 degrees Fahrenheit, which is on the order of 32 degrees Celsius. In Chicago, it's also humid. So it's a warm day in September, and the day-ahead price that the optimizer is being told or given the day before are the blue lines, and the price ranges between $20 and $70 or $68 per megawatt hour. When that day actually materializes, the real-time price tended to be lower at night. In fact, we've seen negative prices that occurred. The optimizer was given the blue prices because those are available a day ahead for the optimizer. When we deploy this problem to an actual office building in Chicago, we see the following. We have a building up here that is in the loop in Chicago of about 100,000 square meters in size, about 1 million square feet. This building was controlled in for a particular day here. Down here on the x-axis you see half hours, so 24 is actually noon. And the Commonwealth Edison peak demand period goes from 9 a.m. to 6 p.m. That's those blue lines. And if we didn't do anything, we would operate the building by starting up systems at 6 a.m. and we would see a daytime peak of about 1800 kW. The optimization found the model that we've built for this building, and the optimization that we applied found a strategy that would start much earlier at 4 a.m. and the black line shows a suggested strategy, and these strategies suggest significant pre-activation of the thermal mass of the building. And since this was deployed in real time, we can actually observe what happened in the black line. The plan was the red line and the actual was the black line. You can see they're nicely on top of each other, not perfect, but the differences are due to model mismatch and prediction uncertainty. But you can see daytime reductions of about 500 kilowatts of afternoon demand for a 100,000 square meter building. That's about 5 watts per square meter or half a watt per square foot in reduction in response to the price signal that you saw previously. So you may ask yourself, well, if the pricing is always low at night and high in the afternoon, could we learn that? Could we come up with a strategy that's as good without having to do the full optimization? And I show you here on this image 3 identical weeks from a weather perspective, but we entertain different pricing structures. And on the right-hand side, you see the price in dollars per megawatt hour, or dollars per kilowatt hour, I apologize. So the green one is the most significant cost shift incentive, whereas down here, the blue one is less so. And in the middle, we have an intermediate to load shifting incentive. One thing you can see is that from the temperature perspective shown on the y-axis, when the price incentives are strong, there is significant amount of activation in the building on one day, but not necessarily the next, right? You can see this Monday, building is pre-cooled significantly, not the next one. The third day, yes, again. So there is some magic to what the outcome of the optimization is, which isn't always easily predictable. If we compare the optimizer against a heuristic that starts pre-cooling the building at the same time of 4 o'clock every day, in all these 3 pricing scenarios, you may wonder, how does that heuristic fare? And it turns out that it fares reasonably well, but the optimizer is better for every day and for every price structure. And so there is a significant motivation to keep on pursuing a real-time optimal approach. One of the problems we're facing with that is, however, that the detailed building performance simulation is a computationally demanding endeavor. And several years ago, one of my PhD students, Peter May Ostendorf, then asked the question, well, could we not do better? And so we started looking at speeding up the process, and the approach is to utilize offline model predictive control, but extract rules that we can detect from the results. And we begin with a model development, and this looks like an offline model, right? No chimney and no people in the building, and we conduct the offline MPC, and we get results. And these results we view as a training set for a rule development and rule extraction and encoding. And the process we adopted was one of supervised learning, where we tried to look hard at the data and find a functional relationship f of x that we could be deriving. And the supervised learning could be used for predicting discrete classes, a classification process, or for regression of continuous variables and continuous outcomes. And we entertained a number of models for this: generalized linear models, classification and regression trees, and boosting tree models. And we utilized these rules f of x. We then tested them in two ways. One, to see how they could perform as their best, and when embedding the rules within the actual building operation. The beauty of these extracted rules is that we can actually convert them to control logic. And this control logic may be of the shape of an if-then rule that could be easily communicated. So for a particular case study, we asked how to open and close the automatic windows of a the automatic windows of a mixed mode building with automatic window control. And what you see in front of you is such a classification and regression tree that was learned from the optimal results. And if you look closely, you can see that the conditions that are used in this decision tree are mostly zone conditions, and if something's true, you go to the left, and if it's false, you go to the right. But basically, the window opening decisions are guided by zone temperature thresholds, and we were able to mimic the optimal results to a good degree. But caution is necessary. We realize that the rules extracted for one location and one building are not necessarily applicable to others. So there is work to be done. So what we learned from this is that we can utilize detailed simulation models, not only for design, but also for real-time building operation. This operation allows us to consider and weigh a complex part of performance and HVAC system trade-offs. We had to work around Energy Plus's lack of state initialization through this replay of history process. I've shown to you a online model predictive control example using a cloud-based software as a service system. That system is able to respond to very complex cost functions with multiple demand charges and multiple additional constraints on the cost function and building operation. And what the optimizer does find is an optimal trade-off between economic incentives and HVAC and building efficiency incentives, and outperforms a heuristic strategy under every case. The idea of extracting rules and to do less heavy lifting computationally is promising, but we are still waiting for the jury to make a decision. In the next study that I'd like to show or discuss here today is we're utilizing rapid inverse gray box models for the purpose of optimizing buildings in multiple energy markets and multiple buildings assembled in a portfolio. And this work was spearheaded by my former student, Greg Pavlak. Considering multiple energy markets, for example, energy market with ancillary grid services is the goal of this. It's a fairly established problem on the power system side, where power plants are operated to maximize profit, but also consider contingency reserves and other operational constraints. Work on this has been done in the vehicle-to-grid optimal charging, where typically linear programs have been solved. Other work in the area of multiple markets has been conducted by former student Pang Zhao, who looked at frequency regulation by modifying duct static pressure set points and zone temperature set points. However, this multi-market scheduling of buildings does face a few challenges. For one, we need to consider occupant thermal, visual, and air quality constraints. We cannot do just everything we would like to do with buildings. And clearly, the building thermal storage is not equal to an electric battery. So it has charge-discharge constraints that we need to consider. And the equipment we utilize, the HVAC equipment, is clearly subject to constraints as well. And the approach we have taken here is to utilize a perturbation method, which basically checks how much frequency regulation can a building offer. Frequency regulation is that service that tries to maintain the grid at a perfect 60 hertz in the US and 50 hertz in most other places in the world. Instead of using a dedicated power plant for that, we utilized the building. We developed a set of reduced order models for this, here shown for a medium office building, where we have a single zone model and a number of HVAC component models around that. So we're not utilizing Energy Plus or a large commercial grade simulation software for that. You can see a good agreement in zone temperatures between the Energy Plus the Energy Plus training data and the simplified model response, especially on the weak end. You can see the free float is in very good agreement. Also in good agreement are the energy consumption and loads for this medium office building. So the perturbation method that I mentioned basically tries to answer the question around a set point, let's say 23 degrees at 1 o'clock in the afternoon, how much could I increase or decrease the electricity consumption in response to a frequency regulation signal. In this case, let's assume we have the fans running at 50%. We have 4 coils, 4 direct expansion coils. 2 are on, 1 is cycling, and 1 is off. By depressing the set point into the blue region or releasing the set point into the red region, we can then achieve, as you can tell, a change in facility electric consumption, which is asymmetric, because in one direction the building floats, and in the other direction we actively depress the building's temperature. If we look at this particular instance, you can see by maintaining the 3 stages of DX cooling on, by raising and lowering the set point, we can achieve a variation in power consumption of plus minus 50 kilowatts. If we extend the allowable number of stages operating, go up to 4 stages operating, or release the 3rd stage and go to 2, we can achieve something on the order of plus minus 100 kilowatts of power consumption change that we can offer in this frequency regulation market. If we do this for an entire day, it could look like this, right? Around 23 degrees temperature set point, we could provide, by changing our zone temperature set points, we could provide a certain amount of frequency regulation that is shown to be around 50 to 80 kW for this building, and it changes over the course of the day, but we could bid this into a market. So the multi-market optimization then involves minimizing a cost function J, which has 3 components. It has a component for the energy cost, for demand penalty, and it has negative a revenue for regulation services, the frequency regulation services we can provide. The energy cost is a function of the day-ahead energy rate, RDA, and the regulation revenue is also a function of the time-dependent regulation price that we're capturing by offering this service. The demand penalty is 0 if we are below a target demand limit, and if we're above a desired target demand limit, it has could have a steep multiplier M, which could drive the problem away from violating this target demand penalty. In an overview of how we then conduct this multi-market optimization, the optimizer tries to minimize this cost function J here, and it finds a candidate control vector X for which the building consumption, energy consumption is than known, but it then takes this decision vector x and explores around it a perturbation of set point changes upward and downward, and those are these deltas, and we get a set of solutions, delta power, the frequency regulation provision, around a candidate strategy, and we can then consider not just the energy minimization or cost minimization, but also consider the opportunity for providing frequency regulation. That all of those terms are considered in the objective function. So if we apply this to a medium office building, and in this medium office building, we assume a high target demand limit, one that is, 1 gigawatts, a number that this building will not achieve. So it becomes irrelevant. And what you see is that the optimizer decides to depress the temperature set point below the upper limit for a good part of the day, so to provide frequency regulation for most of the day. And you can see that clearly in the gray shaded area, and you can see how the building could bid into the frequency regulation grid regulation market over the course of the day. And you can see that the optimizer is willing to spend $23 extra in energy expense, but saves $57 in regulation revenue, or achieves $56 in regulation revenue. The savings by considering frequency regulation for this day go from 2 to 16%. So it's an attractive way of having a building participate both into a time of use dependent or dynamic day-ahead energy market and a frequency regulation market. The prices are, by the way, shown here in the bottom graph, the price for day-ahead energy and regulation. So what happens if in the afternoon we are constrained? We cannot do just everything we want to do. We have a low target demand, and let's say the target demand limit is 325 kilowatts for this building. You can see that for these afternoon hours, we are basically keep maintaining this building under 325 kW. That is less than the baseline operation shown in dashed, but the optimizer stops playing the frequency regulation market pretty much at the beginning of that target demand, or that demand period of the afternoon hours. So when the optimizer has the freedom, it will play in both markets, but if there is a target demand limit, in this case, it costs us $5.50 per kilowatt above 325 kilowatts. So it elects not to participate during that time. So if we have a few buildings, and these buildings are supposed to participate in both energy and frequency regulation markets, we could actually optimize them as a portfolio. And this portfolio view is shown here, where we have a number of buildings, the first two, in fact, where it's desired to include the estimation of frequency regulation potential by those dashed FR rectangles around it. So the simulation results are then passed to the objective function for use in computing the total cost of the control vector. The simulation outputs for these first two buildings, building 1 and 2, are in bold because they are a function of both the initial control vector x and the set point changes delta that we're considering to use to estimate the frequency regulation capability. Okay, so if we have a small set of buildings, we can, in a supervisory fashion, optimize a number of buildings with respect to a number of energy markets. That is a centralized perspective of commercial buildings. For example, in a urban context that is grid constrained, that would be possible to consider a number of office buildings and other buildings in one portfolio. In the next analysis, I'd like to take the perspective of residential buildings, and we're also considering to optimize them. So what you heard today thus far is we've considered commercial buildings because of their size and complexity and the improved economics for advanced controls. At scale, however, residential buildings may effectively respond to utility signals for enhanced grid integration. In this section, we consider how many buildings or many homes, when independently controlled, so unlike the previous study, which was a supervisory and omniscient approach, so if they're independently controlled, can still positively impact our electric distribution feeder level electric demand. And what you have to do here is imagine a smart thermostat in each home receiving once a day instructions on how to adjust the operation and provide grid flexibility. And in this grid flexibility study, we looked at 3 US distribution feeders, one in Houston, one in Los Angeles, one in New York. We utilized Pacific Northwest Laboratories GridLab-D program to model all the components from transformers to lines to lights, and to solve an unbalanced power flow problem for this 3-phase distribution system. We're going to focus on Houston. This Houston feeder has a nominal load of 12 megawatts. It has approximately 2,146 homes on it, and 98% of the homes have an air conditioning system, which is not a surprise to anyone who's visited Houston in the summer. 80% of the total energy consumption is due to homes, and we tackled the problem. This work was done by Chad Corbin. Chad tackled the problem by developing building models. They included envelope model for to estimate the heating and cooling requirements, modeled HVAC equipment, a thermostat, and some simplified end-use models for electric demand from melts and from electric domestic hot water heaters. The RC network for the envelope is shown here on the lower right-hand side. You can see an inside temperature node with an air capacitance. You can see a number of 3 R2C submodels for the roof and for the external walls and the floor. You can see an internal mass node with its associated mass. If we put things together, we are joining models, HVAC models from the ASHRAE toolkit and Energy Plus that we created for this purpose. If we put things together, a single home may respond like I've shown here on the bottom of the chart, where on this hot day, it's 36 degrees Celsius, that's hot and humid in Houston. You can see the cycling of the central air conditioning system in the home over the course of the day. The cycling frequency coincides, or the cycling coincides with the compressor on time. Compressor operates more and more frequently until stage 1 is continuously on. Then people go to work, reset their set points, and but soon after stage 1 is not enough and stage 2 starts the cycle. Things get worse in the evening when people come home and reduce the set point. Now you have the hottest conditions and the highest load. Both compressor stages are running. So you can see a fairly realistic modeling of what's going on in the home, but not just one, but several thousand are being simultaneously modeled. We utilized this model to in a distributed optimization scheme that directs the optimization using a signal that considers the desired electric distribution feeder demand. So imagine a electric feeder that is shown here in red. This is peaking at around 9 megawatts, and if we don't like that, if we like less ramping and less oscillation, especially these 2 ramping events, we could consider this smoother green curve and say that's desirable. So as a result, there are times when we would like the demand to increase and other times where we'd like it to decrease, and the difference is shown here in blue. So this approach generates such a green reference curve for the feeder, and then we transform that feeder reference demand curve into one for each house, and each house then has an optimization engine that minimizes the difference between the current home demand and the reference demand that it's trying to achieve. So we're basically telling the homes when to increase or decrease demand. If we look at the month of July for Houston, when 70% of the homes, of those 2,100 homes, are participating. You can see in the red tone, you can see how we have peakier afternoons. And as July 8th, you can see how the blue curve, or the turquoise curve, is basically filling some noontime valleys. If we focus on a particular day, let's pick the 7th of July, which I have blown up here. You can see in this green tone 50 repetitions of this optimization. So 50 times we're choosing a different set of 70% of the homes, but you can clearly see an improved, a reduced ramping, you can see a peak reduction, and you can see a smoother decline of the rest of the day. If we are adding significant amounts of rooftop solar on these homes, the feeder demand curve looks different. It looks different for every day, and now the optimization is pursuing a different task. If we pick the 1st of July, you can see something that may resemble, with a bit of imagination, the duck curve, right? You can see this potential overproduction here over the course of the day, and the optimized set of buildings are shaving this peak and are filling some valleys. So in this study, we have utilized reduced order models to allow our particle swarm optimization-based model predictive controller to optimize thousands of homes. This residential HVAC direct MPC has actually led in some cases to 3 to 4% more energy use, but we're asking ourselves, is it possible that we're achieving source energy benefits that we wouldn't achieve otherwise? And I'll get to that in a second. These homes are most effective at short-term variations in demand. We're not able to shift demands for long time periods. Oops, I hope this is not. Rajan, I don't know what to do here.
Do you want me to take off the screen for a while till you set up your?
Yeah, something's. I cannot control this little window.
Okay.
Thank you. Okay, I'm back.
Okay.
Okay, thank you. Can you zoom?
Sharing. Yeah, I'm sharing a screen now.
Okay, thank you.
Yeah, we can see it.
Okay, thank you so much, Rajan. I apologize for that. Good. Okay. Well, this methodology that I presented is effective at short-term variations in demand. We are currently investigating the extension to other loads, for example, domestic hot water systems and other controlled devices. We are hopeful that this can be implemented with low hardware requirements for online control. But given the building construction in the US, we are recognizing that we, for one, have right now limitations in terms of the cooling demand that we can actually modify. There's only a limited flexible cooling demand. The timber frame construction has limited storage efficiency, and we're struggling, of course, in any real-time MPC case, we're struggling with forecasting uncertainty and model accuracy issues. So the question that I raised here in a second ago is whether or not there might be source energy benefits by directing a large ensemble of homes to follow a price signal or some kind of utility signal. But without representation of the electric grid system and a joint optimization of both the electric grid and and the building performance, the question of the value of grid flexibility cannot really be answered. So this last section I have to offer is trying to establish this building to grid connection, and it's the first effort in an integrated approach. Currently, we're working on refinements for the US market. The work that we have done here is for our European market together with Lieve Hensen and Dieter Pateu at KU Leuven in Belgium. So how do we combine those things? So the electric grid system is there to provide power to serve a demand. And what I have depicted here is some renewables that at times may be curtailed. And that dashed line here is the time of curtailment. And then we have conventional power plants shown in the dark black line. And the sum of those two are used to serve the demand, which might be lights and equipment and industrial loads. And shown here is a HVAC system. Let's take a heat pump system. So historically, the temperature set points chosen for the homes and for the domestic hot water system would be such that they are basically hovering for the heating case around the lower set points. You can see how the domestic hot water system is cycling to stay there. But what if we were intelligently changing set points and overcharged the building and the domestic hot water system during certain times of the day and then let it flow for the rest of the day? And in this integrated assessment, we're now modifying by changing the demand. We're now changing the conventional power system output in an integrated fashion, shown here as the thin line, and we have avoided the curtailment on the renewable systems. So the hope is that by considering load and supply jointly, we arrive at an integrated model which tells us how to operate the building temperature set points and domestic hot water system. So this is a classical operations research problem. We're trying to minimize the cost of supplying electricity, whereas the cost of renewables is considered to be zero from an operational perspective. So we have some predictions on sun and wind, we have system knowledge, and we phrase the problem as a mixed interlinear program. The optimization is to minimize the cost of running the power plants, and the constraint that we have is an equality constraint where the generation from power plants and the generation from renewables must equal the demand for non-HVAC and HVAC loads. The power plants are subject to cycling constraints, to ramping constraints, and what's new is that the HVAC system is in this problem. So what we actually have is a classical security constraint unit commitment and economic dispatch problem, and we expand it by adding these HVAC constraints. How did we do that? We developed a two-zone model for the home. It's again an RC network model for a day zone and a night zone. We have some ventilation here that you can see. Those ventilation terms lead to some nonlinearity that we had basically a bilinear term that we had to linearize. We could pre-calculate the solar gains and the solar heat gain coefficients. So we then take this RC network model, convert that into a discrete time state space model, do the same for the hot water tank, subject the temperature constraint or the bounds to constraints that are a function of time, and recognize that the heat provided by the heat pump is simply the electricity consumed times the COP in this very simple scenario. What we see is that if we take Belgium as a market and we assume that in the future we will have 30% renewable energy systems, we will renewables penetration, we will have 250,000 residential buildings that are well insulated with underfloor heating and efficient air-to-water heat pumps. So in this future scenario, we have about a peak consumption or a peak system load of 12 gigawatts in Belgium. And if we don't do anything intelligent, you can see how the white renewables, RES is the white area under the dashed line, are leading us to bite into the nuclear power plant operation here. So this is something that we're trying to avoid at all costs. And we're also basically forced to turn down the coal-fired power plant. So this is an operational disaster for any grid operator that we don't want to happen. And the difference between the solid total and the dashed line is what is due to the heat pumps that we're using to serve those 250,000 homes. Under standard operation, we can see the buildings kept at about 20 degrees Celsius and the hot water tank at about 50. Not too interesting. But now if we do this integrated assessment, we can see how by overheating the building at certain points in time and overheating the domestic hot water tank and then floating other times, we can now avoid this nuclear operational nightmare that I mentioned. Even the coal-fired power plants are able to operate a little more as they would like to, but we have greatly changed the way that these heat pumps operate. Here there's a lot of operation. You can see it during this time. There's a lot of operation here, and then there are times where there's next to no operation. So what's the benefit of this? And that is a benefit expressed in terms of curtailment. So how much renewables did we have to curtail before we started the load shaping and afterwards? You can see curtailment is required, so throwing away of wind and solar for many hours of the year, shown in this heat map, from between March to October in the middays. So that's a lot of solar that has to be curtailed. After load shaping, we're now increasing. This is the increase in room temperature control shown here during the winter and spring and fall period, nothing in the summer because the system is not heating in the summer. And if we're increasing the domestic hot water tank, you can see how we increase and overheat that by up to 10 degrees. We are able to reduce curtailment. We're able to throw away less and have more renewables penetration. That is the end of the material. I think what I have shown today is that we have deployed a building energy model for a wide range of complexity, from complex building simulation models with hundreds of parameters to reduced order models with complex HVAC models, and then lastly what you just saw is a very highly simplified state space representation and simplified HVAC systems. We looked at numerous building automation studies from energy minimal control of tabs equipped buildings, price response in commercial buildings in real time, looked at multiple market participation in energy and frequency regulation markets, looked at the role of residential buildings when run by their own smart thermostat, and ended with a view of the value of load flexibility enabled by an integrated end-to-end approach. And it's this last point that is currently going on. We're now extending this investigation on the true value of building to grid integration and demand flexibility. We're trying to find out where is demand flexibility useful, when in time and where in space. It might be useful in Texas, it might not be useful in Colorado, and that is the focus of my current work at the National Renewable Energy Lab and the University of Colorado. So I'd like to say thank you for your interest, and open for questions if there are.
Thank you, Professor. We have 2 questions so far till others get in there. We got a third one also. The first one is from Joseph Chappell. And Joseph, can I unmute you so that you can ask question directly? Do you have a headphone?
Do I see the question?
I can see the question. The question is, just a minute, if he's there, I can unmute him right away. No, he doesn't have a headphone. So anyway, so okay. Joseph wants to ask a question, is that what is meant by phrase state of the shelf? He is new to this particular phrase.
Sure.
State of the shelf.
Okay, that is a little bit colloquial. So state of the art means something is just developed, is available in at research organizations, universities, national labs. State of the shelf is what you find when shopping at a store and the products you find on the shelf. So I should have been less colloquial, but a state-of-the-art product is something that was just released and represents the latest knowledge. State of the shelf is something that represents established knowledge and is no longer cutting edge and novel. That's all.
Thanks. Sadaf has a question. Sadaf, I have unmuted you. You may ask a question directly.
Hi, can you listen me?
Yes, we can.
I can hear you. Yeah.
Okay. Good morning, Professor Henze. First of all, thank you very much for such an enlightening talk. And my question is, like, which software have you used for these RM models, and which approach you have used for developing these RM models?
So the reduced order models have basically all been, the coding has been done in MATLAB. That is what has been most productive in my group so far is MATLAB. But increasingly, we're transitioning to an open source modeling environment such as Python.
Mm-hmm. Okay. And like, is this resistance capacitance models, and were these models adopted from someone, like some other work or something like that?
Yeah, sure. I mean, inverse gray box modeling and reduced order modeling has been around for a long, long time now. Mm-hmm. So I don't think we've done anything groundbreakingly new there. But this, a lot of the single zone models that we're using very, very successfully are based on the so-called simple hourly method by the EN ISO 13790 standard. So that's 13790. Simple hourly method model. That modifications to that or direct use of that have proven to be surprisingly powerful and surprisingly simple. So if you were to be interested in conducting some reduced order modeling for some rapid prototyping or for some controls application, I would recommend the simple hourly method.
Okay, and second question. Just a simple question: that is, these models were calibrated?
Yeah. So there are two calibrations. So for the offline MPC studies, whenever we whenever we utilized a reduced order model, we would use surrogate data from a complete model. For example, an energy plus model. We had these complex models available, and then we trained from these reference models, energy plus reference model for a retail store, for a large office building, we trained the inverse gray box models. In the case of the real-time or online MPC case that I presented, we actually took a energy plus model and calibrated it against real data and real building data, because that building in Chicago is an actual building, and we had to develop a multi-zone representation and had to calibrate that model.
Okay, thanks. We have 3 more questions. Third one is from Brad Clifford, and he wants me to ask this question, so I'll just read it out.
Sure.
Can you touch on how we use predictive modeling for a new construction versus existing buildings, and your thoughts on accepted trends?
Yeah. I think increasingly in the past, building energy modeling was not consistently utilized in designing buildings. Increasingly, building models are developed, and predictive modeling for operational purposes is what I believe to be the holy grail, in the sense that we are spending the money and effort on developing design models, and we then carry them into the real operation of the building. We continuously tune those models. We compare design intent against actual building performance, and it is to do that is easiest when you are dealing with a new building for which a model was commissioned and the money was spent to actually come up with a detailed model. For the existing building stock, we are recognizing that conducting these in-depth audits and detailed model calibration processes is very time-consuming and costly, which is the reason that for the online MPC, the software as a service that I presented, we've been working very hard at rapid modeling tools, allowing us to quickly arrive at a model that doesn't require weeks of engineering efforts. And we have certain categories of buildings, large office buildings, that after a while we have kind of a library of models that we can modify into, so it doesn't take as long. But I would say it's a pretty significant hurdle to convince a building owner to invest in the development of a detailed and calibrated building energy model for operational purposes if that model hasn't existed in the past for design purposes. But my point is, as we're designing buildings more and more with the help of simulation tools, it should be a natural to extend the life of our models into the real operation.
Thanks. We have a question from Mark Pauls. Mark, would you like to ask a question?
Yeah, can you hear me okay?
We can.
Oh, perfect. Yeah.
Okay. Thanks very much for the presentation, Professor Hense. It was very interesting, particularly in relation to my work at a high-performance office building up in Canada that has a lot of metering opportunities, and we can implement some of these ideas, I think, as a kind of as a test case. And I'm curious to know a little bit more about the MATLAB optimizer. You mentioned in the first paper you presented that there's an optimizer that takes in some inputs, creates some outputs that then is generated or generates outputs that are used for the Energy Plus model and then fed back into the building automation system. But I'm curious about that optimizer itself. Can you say a little bit more about that?
Yeah, we have tried a lot, and we've had a lot of, ended up having a lot of good luck with Aberhart and Kennedy's particle swarm optimization. And in my group, we have taken these ideas and modified the PSO, the particle swarm optimization, to maintain a variable and adjustable number of neighborhoods. So we don't only have one swarm, we have multiple swarms. And we have, in addition, developed or modified the PSO to consider a parallelized environment in which we can rely on many computing nodes. So those two changes. But in general, an optimizer does not rely on any gradient information, has worked well for us. We've also tried genetic algorithms, but have fared, and some quasi-Newton methods, but we've fared very well with the PSO approach, and that's a simple algorithm, and we've made it just better in our group.
We have a question from Marco, and I need to read that out. The question is, for optimizing white box models, how many parameters were optimized and what is the cloud computation power? Why did you choose first hour forecast? Could you have used, for instance, day ahead forecast and day ahead implementation? I'm just reading it out. Yeah.
Okay. So we have used just the Amazon's Elastic Cloud 2 as a compute resource. We're basically working with commodity cloud computing capabilities. We do not purchase more powerful machines. The optimizations variables, or excuse me, the manipulated variables that we optimize include just global temperature set points in some cases, but they also include pump operation, they include HVAC system availability, and we are free to include and exclude as many as we want. It turns out that if we have a detailed building energy model by properly optimizing just the global temperature set point, we can in turn activate the building automation strategy that is in the model. So if the model has a particular chiller sequence or a particular operational approach to the hot water plant or the chilled water plant or to the air handlers, simply changing the set points will lead to a proper modification of the strategy. The optimization is typically conducted by day-ahead forecasts, so we take into account the information for the next day or two, and then the strategy in the true receding horizon MPC, we would just implement the first optimal step. The first optimal action of the strategy would be sent to the building. In offline studies, we could implement the entire day because nothing really changes and we have perfect knowledge. But in real-time control, we forecast the next day. So we have the next day's weather, pricing, and building utilization information, and we implement just the first set point or the first control vector for the first hour, and do that in a receding fashion.
Okay, thank you. And now we have a last question from Ali Saberi. Ali, I have unmuted you, and you can ask a question directly to the professor.
Okay.
Ali, can you hear us? Ali? Okay, let me read out the question. The question is, what type of optimization technique you use to develop reduced order model and also MPC? Is there any general guideline you can recommend as to which optimization technique to use for different scenarios?
Mm-hmm. Yeah, I think the second question I tried to answer. So we have tried a number of gradient-based and gradient-free optimization techniques, and I would say that for those who are interested in getting started, a gradient-free approach like particle swarm optimization is a good start. So I think that answers the second question. The inverse or the reduced order modeling, Greg Pavlik, one of my past PhD students, has actually set up a nice approach in which a single zone cavity model was modeled in increasing levels of complexity. It started with a 5-parameter model that had 4 resistances and 1 capacitance. That is actually the simple hourly method that I mentioned earlier. And then he went from that to an 8-parameter model, then to 11, then to 13, and so forth, all the way to a fairly complex envelope model with 21 parameters and a number of resistances and capacitances. And by training these models on training data and testing them on validation data, you can compare the model complexity against each other. And there's actually a metric that you can use, is the generalized cross-validation index, GCV, that would tell you, you know what, under these circumstances for this building, the lighter model, the 8-parameter model, is actually better than the 21-parameter model. There are other techniques that you can apply to decide on model complexity that are more in the vein of typical information criteria, like Bayesian and Akaiki's information criterion, but you can develop a number of RC models, and you can then deploy or apply the GCV, the Generalized Cross-Validation Index, to get a recommendation of what model complexity is required. And the techniques behind this typically involve utilizing RC, inverse gray box modeling, that is somehow physically motivated, so the resistances and the capacitances have some physical interpretation, and the envelope model is then coupled to HVAC models for heating and cooling systems, and those could be of, you know, very simple models where you just have an efficiency or a COP, or you could go to the literature, look at the ASHRAE the Energy Plus engineering reference, or the AshRay Toolkit 2 to learn about useful models. There's a bit of literature out there on what models one could utilize, but it's typically the envelope is modeled in some kind of a resistance capacitance equivalent network structure, and then the system models are performance maps that there's quite a bit of literature out there already. So I hope that answers the question.
I assume so. Thank you. We don't have any other question from the audience. So I wish to wrap up this webinar. Thank you, Professor, very much for offering this webinar. It was very insightful. And thanks audience for attending this. Hopefully people would be attending IBPSA conference and also future webinars. The next webinar is scheduled on July 22nd on urban scale modeling. So please check out the website soon. Thank you, Professor. Thank you all.
Thank you all for attending. Have a good day. Bye-bye.
Bye.